Now, that's our aim, isn't it? Try to understand thermodynamic behavior of large systems or systems involving large number of particles, although in our daily everyday life, the large system may be a gram of a material, could be a gas or liquid. So this is the most important thing you should know, isn't it? To have a mental picture of what should be done to calculate, to find the important properties of your system, starting from this microscopic ideas about the system, isn't it? We have done that for certain systems and we are going to repeat that. Well, we have discussed that the total number of states, available states to your system can be written as a function of macroscopic variables, total number of particles in the system, volume, and energy of the system. And of course, the entropy will also be the function of same variables, and it will be given by kV ln omega and V. Now let's take the intensive variables as temperature, pressure, and chemical potential. The last thing is the chemical potential we have defined in the previous lecture or discussed. Of course, you can get the pressure, temperature, and chemical potential from the entropy. We know the relationships, isn't it? For example, that is 1 over the temperature from your thermodynamics. Huh? And derivative with respect to volume keeping and an E constant gives you what? Pressure, of course, over temperature, and del S del N, keeping volume and energy constant, is minus mu over T. Okay? Well, we can do that to get our pressure, for example, isn't it? Using entropy. Or we might have energy at hand, total energy of the system, E, but we can turn this into a set of equations that will give us the thermodynamics if we know the energy instead of the entropy. So, alternatively then, we can write, well, pressure is del S del V and E del S del E and V. V you can write that as minus del E del V, keeping N and S constant. Well, you can get this last relationship from the first law of thermodynamics, isn't it? dE is equal to TdS minus PdV plus mu dN in most general form. So if you keep N and S constant, you can get it by taking a derivative of energy with respect to volume. Now, can you tell me any difficulty in using this relationship? When can you use it? Is there, well, I can get pressure from taking derivative of total energy with respect to volume, keeping N and S constant, negative of it, isn't it? I can do that. But what is the difficulty with that? Can you see any difficulty in doing that calculation? You don't. How can you keep entropy constant? That's the problem, isn't it? You can keep number of particles and volume constant. I mean, you can even do that, try to do that experimentally, but how are you going to keep the entropy constant? That's a problem, isn't it? If you know that you have an adiabatic process or a system isolated from the rest, no energy exchange, you can say entropy is already constant, so I can use that relationship. But other than that, you should make sure that the entropy is really constant, is kept constant in taking that derivative. That's the important difficulty. So you should try to look at these relationships with a practical point of view. You have to ask yourself, can I do that, etc. Similarly, you can get the chemical potential as del E del N, keeping V and S constant. And of course, the temperature, we can invert that relation, is dE ds N and V. Read Appendix H of your book so as to see that if X, Y, and Z are mutually related, then del X del Y, keeping Z constant, times del Y del Z, keeping X constant, then Z, then X keeping Y constant is -1. You can use that relationship to change your variables. So you make a transformation from one set to another. Okay? Of course, with this, rest of the thermodynamics follows. Well, for example, you can get Helmholtz free energy some books call it A, including your book, I think. Some books call it F. It is nothing but E minus Ts by definition. Huh? Helmholtz free energy, you remember that. Recall this. Gibbs free energy. G is defined as A plus PV, or E minus Ts plus PV, Gibbs free energy. Okay? That's the definition of Gibbs free energy. And you already knew or learned that this is mu times N. So that's also another way of looking at the chemical potential as Gibbs free energy per particle. Mu is G over N. It is a measure of what? Now I want you to think about these relations as physical properties of a system. For example, mu is given as del E del N. Delta E, delta N. What does that relation tell you? It should tell you something. It is not a very simple derivative. You cannot only look at them as simple derivatives. They are, but physically you can look at it and say, well, chemical potential is nothing but the change in energy or energy required to change the number of particles in the system. Change in energy when you change the number of particles. Delta E divided by delta N, isn't it? So you should learn how to look at these, not only simple derivatives, but also physical quantities. They are physical quantities. They have information carried with them. Well, we have other thermodynamic quantities like response functions. Well, along with enthalpy, we have to remember that too. Here is the definition. E plus PV. See certain parts of these Gibbs free energy. E plus PV is known as enthalpy, or G plus Ts, if you like. And response functions come as heat capacity at constant volume, which is defined as T ds dt, keeping N and B constant. Can you tell me physically what this means? TdS is d bar Q, isn't it? Heat given to the system. And this is change in temperature of the system. So what is that measuring? What is the response function known as heat capacity? Isn't it, well, when you give heat, how much the temperature of the substance or the system will change, isn't it? It is physically more intuitive if you think that way. So if you give heat and temperature is not changing, what is the heat capacity of a system like this? Delta T is 0 when TDS is non-zero. What is C? Something divided by 0. What is that? Infinity. So if you give heat to a system and its temperature is not changing, it has infinite heat capacity. Like in the case of a bottle of hot water thrown into the sea. A bottle, can it change the temperature of the sea? No. It has infinite heat capacity in that sense. So we call those systems heat reservoirs or heat bath. Okay? Heat reservoir or heat bath. Take out some heat, its temperature will not change. Add some heat, its temperature will not change. Okay? That's the heat reservoir. Well, of course, this will turn out to be del E del T, keeping N and V constant. If you keep V constant, dV will be 0, isn't it? Very simple. On the other hand, heat capacity or specific heat, depending on whether you talk about the system or per particle, at constant pressure, on the other hand, will be the same definition, but this time keeping pressure constant. This is going to be then E plus PV then T, N and P, and that is nothing but enthalpy. So in other words, you have a well-defined path from entropy to the other thermodynamic properties of your system. By taking derivatives of entropy, you can derive other thermodynamic properties. So all you have to learn is, if you have one of these quantities, how to derive the thermodynamics. That must be your plan, mental plan, that will be very useful in exams, for example. Now, let me go to probabilities and averages and such things, because we are dealing with large systems, and those are the things that we can do, as you have learned in statistical thermodynamics. We can only talk about average quantities. If there are lots of particles, we cannot even write their positions on a piece of paper, well, a collection of papers. 10 to 23 particles, all the papers on Earth will not be enough to write them, isn't it? If you write 3 numbers, X, Y, Z, coordinates of a position of a particle, imagine how much paper you need for 10 to 23 particles. A gram of copper, for example. So we are going to deal with averages, and of course, to be able to get averages, we have to know probabilities of certain quantities having certain values, okay? So statistical mechanics is a mathematical structure in that sense. So this is the statistical part. Mechanics we can do. Energies, etc. Momentum, laws of mechanics. Now statistics. Let's discuss probabilities a little bit. What is the probability? Well, we said if the system is in equilibrium, the probability of finding the system in any one of its microstates are equal. But what is the probability of finding the system in a specific state with a specific energy, isn't it? That's our aim now. For this, to be able to discuss this, we have to specify our system. Now, we are going to specify our system in 3 groups. One group will be systems which are isolated. No exchange of energy or particles with the rest of the universe. An isolated system, okay? Then the next system that we are going to study is systems that will interact with the rest of the universe or with a heat reservoir, to be specific, by exchanging energy only, okay? And third group of systems are systems that interact with a heat reservoir and a particle reservoir. So it can exchange energy and particles at the same time, okay? So we can exhaust our chances by doing this. If you studied these 3 types of systems, we are dealing with all the systems that can be met in the experiments, isn't it? So let's start with the first type of system, isolated system. Let's write the probability of finding the system in any one of the microstates available to it. Isolated systems are called microcanonical. So probabilities and averages. So we are in some sense taking into account interactions between systems in this case, isn't it? An interaction that results in energy exchange, an interaction that results in both energy and particle exchange. Well, the first type of system is isolated. We said that for an isolated system, all microstates are equally probable, isn't it? That's what we said as our postulate number 1. If all microstates are equally probable, what is the probability of occurrence of a microstate? Then probability of occurrence of a given microstate. It's very simple. Let me call it probability of finding the system in a specific microstate R. This is nothing but, if the total number of states is omega, it is 1 over omega, isn't it? Very simple. If you have 6 states available to your particle or system, it's 1 over 6 to find it in any one of these equally probable microstates. That is our probability. It's a constant depending on total number of available states, microstates to your system. Well, we call these systems microcanonical, as you recall. Now let's consider systems interacting with a heat reservoir by exchanging energy in the form of heat and nothing else. So the second group of systems interacting with the heat reservoir by exchanging energy only. Do you know what we call these systems? Canonical. Canonical systems. So let's see what is the probability for our system to have a specific, to be in a microstate with energy epsilon. So the system we are dealing with is that system, that subsystem. It is interacting with the heat reservoir. Our system has omega number of microstates. Heat bath, heat reservoir has a number of microstates omega B at temperature T. Now, of course, if our system is at a higher temperature, there will be heat flow from our system to the heat reservoir. Otherwise, there will be heat transfer from the bath to our system. So temperature gradient decides in which way the energy will be transferred. Let's take this total system, bath, and our system that we are studying as a single system which is isolated, isn't it? These double walls are telling us they are isolated. They are interacting with each other, and both are isolated. Well, let's imagine that the total energy of this is E sub T. Now let's try to derive the probability of having the system in a specific microstate available to it, whose number is omega, okay, of these microstates. Well, total number of microstates available to both of these systems, our system and the heat reservoir, is nothing but the multiplication of these corresponding numbers, isn't it? That's the total number of available microstates to the collection of these two, heat bath and our system. Well, we know the energies, corresponding energies. So if the total energy is E sub T, and the energy that we are looking at or looking for our system is epsilon, so the question, our question is, what is the probability of finding our system in a microstate with energy epsilon? Isn't it? That's what we are looking for. But total number of microstates available to the combined system is multiplication of these two numbers. Is that clear? Okay. Now, then the probability of our system having the specific energy will be proportional to this multiplication, isn't it? Total number of states available to system. But this is equal to 1 because we are interested in finding our system in this specific state, one single state. We are asking that probability. Huh? Is that clear? Probability of finding our system in a very specific state with energy epsilon. So the number that we have to consider for our system is one state only. So this leaves us with a probability which is proportional to the number of microstates available to the heat bath with that energy, reduced energy. And of course, we know that the entropy is given by kV ln, total number available to your system. And we can invert this by exponentiate both sides. We can invert this by writing omega equals to e to the s over kv, isn't it? Logarithm. When you invert the logarithm, you get exponential like this, isn't it? So subsystem, our subsystem, let's call it our system, not the heat bath, is very small. That means epsilon is very much smaller than total energy available to both, or the sum of both energies. So we can Taylor expand our entropy. How are we going to do that? Well, our entropy in question is corresponding to that specific energy. number of state is proportional to that. So you can expand this about total energy. The first term is S of ET, and the second term E del S del E plus etc. Well, I'm a little bit sloppy now in writing these expansions, but we know this quantity, del S del E. What was this? 1 over the temperature, is it? So that is equal to 1 over the temperature. So we have, as first correction to this term, because the other terms will be proportional to E square, E cube, etc. But epsilon is very small, its square is even much more smaller. So that becomes S ET minus E over T. So I hope this will help you to recall what you have done in undergraduate course. Well, if that is the case, we can get the probability. Let's write it here. The probability then of finding the subsystem at microstate, in a microstate with energy epsilon, is going to be proportional to e to the SET over KB times e to the minus e over KBT. Isn't it? The second term in the expansion is epsilon over T. Epsilon is energy, of course. Huh? Well, this is simply a constant, isn't it? Why I keep saying proportional but not writing equal? Because I have to normalize these probabilities, isn't it? When I sum them up over all possibilities, I have to find one. So if that is the constant, then the probability of finding my subsystem in a microstate with energy E or epsilon is proportional to e to the minus e over KBT. Have you seen this factor before? Of course, this is what? Boltzmann function, or Boltzmann factor. It can also be said Boltzmann distribution function or canonical distribution function, isn't it? Exponential e over KBT. Now, let's try to normalize this. If the probability is proportional to exponential factor like that for a canonical system, we can imagine that we have a collection of energies available to our system. We can specify each possible energy as E sub r, or epsilon 1, epsilon 2, epsilon 3, etc. Possible states available to our system. Then probability of finding the system in a state with quantum numbers R, let's say, is proportional to e to the minus ER over KBT. KBT is energy, isn't it? Corresponding to the temperature T. Well, normalization means if I sum all of these probabilities, I have to get 1. If normalized, how am I going to normalize this? Well, I can write the following. Now, if I sum this, okay, sum over R divided by sum over R, I get 1. So that's the way to normalize the probabilities. So this is the exact expression. Now it is equality of finding my system in a specific microstate with energy epsilon R. Is this clear? Do you have any questions? No questions? Usually I beg for questions in my classes. I don't know why. So please ask me a question. Well, this is called the probability of finding the canonical system in a microstate with energy ER. How are you going to go from here to averages? An average value of any quantity. Let's take the average energy of the system. Let's denote that by e to the bar. What is the average? If energy values are ER and the probability of having that value is PR, it is simply multiplying probabilities with the corresponding energies and summing up, isn't it? That's the average value. Since you are summing over all the possible microstates, you are getting average energy for your system. Do you recall this from your earlier course? Now it's getting blurred a little bit. But I'm sure you have done that. I'm sure you should have done that, because we can do nothing but take averages, talk about average quantities, isn't it? So if in this expression I use that, I am doing average energy for a canonical system who is exchanging energy with the heat reservoir. So I know how to find the average energy of that system. In equilibrium, of course, there's no more exchange of energy with the heat bath, isn't it? And the temperatures of your system and the heat bath will be the same. The energy exchange, we have just tried that, will continue till the temperatures of your system and the heat vat will be equal, then there's no energy exchange. Equilibrium is established. Okay. Any question with this? Again? No? Let me do the last thing, and with this I think you can do marvelous calculations, because you know everything now. You know the probabilities, you know how to take averages. If this is a general quantity, average of a general quantity is again summing over all possible microstates, PR, and the individual values of that quantity. That's something you should never forget. If you are my students and you graduate from this course, if somebody asks you, I will never forget you if you forget this. I will never forgive you for this. Okay. Now let's take the last type of systems, which are, well, both exchanging energy and particles with a reservoir. Energy and particle reservoir. This is the most general case, but I will do that after 10 minutes break. Thank you.